Hello students, in this video we are going to learn about capacitance of a conductor. It is very important concept for capacitance as well as for the capacitors. Now we begin with a charge which is given to a conductor. We know that it is difficult to handle free point charges or hold them fixed in any desired position. The only practical way to handle charge would be to put it on a conductor. So, we are going to start here. The charge Q is given to a conductor. And hence the potential V is developed. I just draw a small diagram to understand this. Here is a charge which is given and the potential V, and the charge is distributed in this given diagram as shown here. Okay, so the potential V is directly proportional to the charge given, and we can start this here. In order to remove the proportionality sign, we can substitute a constant. This C is what here we are writing. This is equal to Q by C, and therefore C is going to be Q by V. What is C here? It is the capacitance. It is the capacitance, that is the ability to store charges, the ability to store electric charges or electric potential energy. This is introduction for capacitance of a conductor, where C is nothing but the capacitance. It is the ability to store charges. If Q by V is a formula, so we can comfortably write what is the unit of this. We are writing here, it is given in the unit of farad. We can also write capital F for this. And this is going to be 1 coulomb upon 1 volt, that is equal to C V minus 1. We can also use, in the practical applications, we can use here 10 power minus 3, 10 power minus 6, that is the microfarad, millifarad, microfarad, and also nanofarad, 10 power minus 12, picofarad, etc. In smaller units of farad, we can use it. So what is the capacitance? It is the ability, as we have discussed. So we can also make such arrangements in order to study here capacitors. Capacitor, it is an arrangement, or we simply say it is a device. It is an arrangement of two conductors. Two conductors which are given with the charge Q. One may be plus Q in one conductor. We just see here two such conductors we have taken. One is given positive and minus, and here, and hence the net charge anyhow is going to be 0, because we say here the charge Q is being given. That is nothing but here in this configuration it will be taken by the two conductors, and the potential difference will be V1 and V2 respectively, and V1 and V2, so the difference will be V1 minus V2. And it is nothing but the arrangement of two conductors of different potential, charge and size and shape, but definitely they are going to be separated by certain distance. Definite distance should be there relative to each other. It can also be the conductor of this shape I have taken in this order, of any size and shape. But the capacitor, the ability to store charges, it depends on the nature of the medium around this, the nature of the material medium around this. And also it depends on size and shape of the plates. Plates means the conductor. And also it depends on the presence of any other conductor around it. That's very important. If you keep one more like this, what is that nature of that conductor? Okay, but it does not depend on the material with which it is made actually, because it depends on the material medium around this. Therefore, we can also express this in the circuit diagram in this order. Look at this. In the circuit diagram, we write the fixed capacitor in this order and the variable capacitor by showing this arrow in this. Variable capacitor. This is for the symbol for the circuit diagrams. This is introduction for capacitance of a conductor and the capacity. That is nothing but the capacitors are the arrangements of two such conductors. I hope you have learned. Now, let us proceed to the principle of a capacitor. How can we charge a capacitor? Charging of a capacitor is nothing but transferring the charges. You can look at this. We have taken one of the capacitors in parallel plate. We also have to remind this is nothing but the types of capacitors. There are different types. We can say spherical capacitor, cylindrical capacitor, and also parallel plate capacitor, which is drawn in front of you now. There are different types. Practically, we use parallel plate capacitor most of the cases. So here, two such plates, the conductors are taken, and one is completely charged, another one is uncharged initially. And this is brought very close to the charged conductor, the plate, which is completely positively charged. And we know due to electrostatic induction, the charges are induced here in the second plate. Negative charges are induced because it is positive. On the other side of it, positive charges are induced. You can look at this in the diagram. Due to electrostatic induction. And these negative charges anyhow going to decrease the potential of this first plate. In the second plate, negative charges decrease the potential. But this positive charges may increase its capacitance, its ability to store charges, but here they are far from this plate. And now look at this second arrangement. The same plates are taken once again, and here same positive and negative, but this side of the second plate is given with the earth connection in order to bring all these charges to the earth, that is to get neutralized, and these negative charges will remain here. And therefore, this ability of storing the charges will increase as long as it is positively charged. As long as it is positively charged, the negative charges are induced and these positive charges would go to the earth. And this is nothing but charging of a capacitor. This is going to be principle of a capacitor. Once it reaches its saturation level, it will also discharge. Discharging of the capacitor will also happen. So, we have learnt about principle of a capacitor in this manner. Let us see here the capacitance of parallel plate capacitor. In front of you, the two plates which are given, the same arrangement is kept in this order with the positive plus charge density and minus charge density. And here you can see the arrows that shows uniform electric field. Uniform electric field, and the distance between the two plates is D here. We have taken. It is of area A. Each plate has an area of cross section A, and the electric field is from positive to negative. And as we have already discussed also in the previous cases under Gauss theorem, what is that? When two such parallel plates are kept here and the electric field outside the two plates, that is the region 1 and region 3, we have already learned the electric field is going to be 0. The electric field in between is nothing but sigma by epsilon naught. It is nothing but, we already know that sigma by 2 epsilon naught plus sigma by 2 epsilon naught is going to be sigma by epsilon naught. This condition we have already discussed also. This is the information about parallel plates. Two parallel plates which are arranged in this order. Now we have to discuss about one more point here. This D square is much less than the area of cross section, and hence you will get such uniform electric field. If this is greater, okay, if this is given definite finite value, if the area is given with the finite value, what would happen here? You may get fringing of the field. If it is given the definite area, then the fringing of the field, what is that? The electric field would go outward. Okay, at the edges it would go outward instead of forming the uniform field. So now we have to learn what is the potential difference developed between the two parallel plates, between the parallel plates kept in front of you. So here we arrange this V is the potential difference that is going to be, we have to take this order. V is going to be electric field which is produced, that is sigma by epsilon naught, which we have taken, multiplied by distance between the two plates. Distance between the two plates. Distance is D. Therefore, we can write E vector and the distance what we have taken here as D. And this E can also be substituted. We have the formula epsilon by sigma by epsilon naught into D. and this is the potential difference. Therefore, we can also write this sigma in the next step. I write for the sigma value, the charge density. The charge density can also be written here as a Q by A d upon epsilon naught. Sigma by epsilon naught d, that is what written here, Q by A for sigma value, the charge density. And therefore, we can write this is the expression for the potential difference. But we are talking about what is the capacitance between the two parallel plates in this given arrangement. Therefore, C can also be written here upon Q by V. Okay, and when you substitute this equation number 1, you may get this order. After cancelling the terms, you will be getting here epsilon naught A by D. After substituting this equation 1 here, you must be getting the capacitance of this order. This is a final expression for capacitance, where C is equal to epsilon naught A upon D. It shows that here the capacitance of this arrangement or the capacitance of a capacitor, it is inversely proportional to the distance between the two plates for the parallel plate capacitor. If the distance increases, the capacitance would go less. And it also depends upon the area of cross section of the plates. And as I said, it depends upon the material medium around the plates. Okay, so this is the introduction given for capacitance of parallel plate capacitor. We have discussed about principle of a capacitor, and also we have learnt about introduction of capacitance. Hope you all understood. Thank you for watching.